Welcome. We're going to be exploring volcanic mountains in this lab, and I wanted to give you an introduction to some of the terms, concepts, and preview some of the skill sets which are a little bit tricky, especially if you've never worked with topographic maps. So when we think about volcanoes, there is a relationship between the shape of the mountain, the type of eruption, and the mineral composition of the magma. And so, as you can see here, that there is a relationship between viscosity of lava, mineral composition, and temperature as well. So think of viscosity as thickness, and it has to do with the nature of material. And so if you think about how honey would flow across your countertop versus peanut butter, if they were both poured out, peanut butter is much more viscous than honey, and so that's a good way to think of that property. So lava with very little silica forms volcanic rock basalt, and this tends to be quite fluid, and basaltic lava is effusive or relatively quiet, non-explosive eruptions. This is characteristic of the Hawaiian volcanoes. And you can see in the images here that there is lava that is moving across broad swipes of the landscape and going through a residential area and across some agricultural fields, and then in this example here, down into the ocean. And it tends to be relatively slow moving and very destructive, but it's different than the other type, which is where we get lava with greater amounts of silica. This tends to be more viscous, and examples are andesite and rhyolite. The gas bubbles will rise slowly beneath the surface. As the magma moves towards the surface of the earth, there's an increase in pressure, and this leads to explosions. And these explosions include ejection of pyroclastics, and pyroclastics are solid pieces of shattered volcanic rock. So here are some examples of this type of volcanic explosion, and you can see quite a large cloud with dust and soot and these pyroclastics. And here's one with some cloud material, smoke, soot, dust, and the pyroclastics, as well as some of that lava, the molten magma, melted rock. And then here is an example of the same kind of volcano in a snow-covered area. Okay, there are 4 basic types of volcanic mountains that are described in your lab manual. Please be aware that there can be different categorizations depending upon what reference you're using. But for our lab, we're going to consider shield, composite, plug dome, which is also known as lava dome, and cinder cones. And here are just some representative pictures of a shield volcano, a composite, a plug dome, lava dome, or a cinder cone. So let's take a look at cross sections of each of these types of volcanoes, and we'll start off with a comparison of side to side, and then we'll get into some more detailed examples. And so if you look at these differences, you can see shield volcanoes have a low profile, and then a dome volcano or a plug dome has a larger profile, and there is a slow extrusion of viscous lava from it. Moving on to this third example here is a caldera volcano, and this is the caldera that you can see in between these 2 larger peaks or cones, and you can see here a representation of how those cones develop. And so as the magma chamber empties, the center of the volcano begins to collapse, and that's where you get the caldera. And then again, in this example, there's a composite volcano here on the right, and it's built up by many layers. And so imagine that if you cut a slice through the middle of that volcano and were able to get a cross-section view, you could see these layers of hardened lava next to the pumice and the ash, which would be softer and looser in composition, and then the lava coming up through the center of the mountain, and through these eruptions, it's going to come out and lay down more layers. Okay, let's take a look at a few more details. So a shield volcano tends to erupt basalt lava, and this basalt lava has a low viscosity, so it's more watery. Thinking back to our example, it would be more like honey than like peanut butter. It can flow on the surface better. And then when these volcanoes erupt, they tend to spread out over very large distances. Again, very indicative of the volcanic activity that you will find in the Hawaiian Islands. And you can actually walk out to places on the islands in Hawaii where the lava is flowing. And you can see it entering into the ocean. And so it's continuously happening, and there are more active periods, certainly, but it is something that's pretty spectacular if you ever get a chance to see it. I've walked on many volcanoes, and I have flown over volcanoes when I was studying in the Hawaiian Islands. So here are just some of the parts of a shield volcano. Take special note of the lava flow, and there's something called a flow field. Lava tubes are areas that have different openings um, and different stages of the hardening of the lava. And then there is obviously the ash and the gas cloud is present with this kind of volcano as well. And there's the origin of that molten rock. Okay. The second type is a composite or a stratovolcano, and these are built of layers of viscous material rather than fluid lava. They tend to form tall peaks rather than rounded cones because of this way that they're formed. The summit can sometimes collapse into a caldera, and composite volcanoes are responsible for the most catastrophic eruptions in history. There's a lot of damage. There is an eruption cloud, and not only is there the fallout and the flow of the lava in the close proximity to the location of the magma and the chamber and the vent, but there is quite a large area affected by ash and acid rain after the volcano erupts. There can also be landslides and other related hydrothermal explosions. This right here, I want to point out to you, is a lava dome, and they're very common on the side of a volcano or mountain, and they are areas where the pressure builds up and there are explosions there as well. There are places in the world where you can see composite or stratovolcanoes. One of note is Mount Arenal in Costa Rica. There's quite a steady tourism trade and scientists that go out to study that volcano, and you can get quite close to those as well. I've actually camped at the base of the mountain, and we were able to not only see and hear, but we could feel the eruptions, and they were happening about every 2 hours, and they were small compared to catastrophic worldwide events, but they were pretty spectacular. So again, I encourage you, if you can get out in this world, to try to safely explore some of these features. Okay, so stratovolcanoes build up on height by layering the lava, ash, and tephra. And so by this definition, there's alternating layers of pyroclastics and lava. When the ash falls and the lava flows, it solidifies and it makes a narrow cone. And the lava has high viscosity, so it runs fast and freely, and it becomes a steep-sided cone. And Cone-shaped volcanoes are also known as stratovolcanoes, and they're built from many layers of lava, pumice, ash, and tephra. Here's an example of another type, a plug dome or lava dome. When the lava is very thick and sticky, it will pile up around the vent, and this forms a dome. And you get circular mounds that protrude from the volcanoes, and this is because of the slow release of viscous lava. And so you will see that the dome tends to be smaller and a little bit different shape than if you were looking at a composite volcano. With a cinder cone, they're also called spatter cones. And this is the most common type of volcano in the world, and they're small in comparison to other types of volcanoes. So they can be tens to hundreds of meters in size, and at the same time, they're very steep with a bowl-shaped crater at the summit. And the cinder cone volcanoes are shaped like a conical hill with high slopes. They have a conduit and a magma chamber, and you can see here is a cross-section of a cinder cone. In this map, you're going to be exploring, in this lab, you're going to be exploring some topographic maps. And this is a representative map of Hawaii. These are found in the back of your workbook, and the specific numbering can be found in the directions. And you're going to be measuring gradient. It's a simple way to compare the steepness of slopes. A way to define gradient is feet of elevation change per mile. This is in words, and here is the equation from your workbook. So you take the elevation change in feet, divide that by the number of miles, and the resultant gradient has the units of feet per mile. Make sure that you remember units. It's very important in science. There are very, very few things that are unitless. If you're talking about ratios and numbers that are related to indices or an index, you can have unitless numbers, but that's very rare in science. And so make sure you do keep track of your units. Here are the steps that you will use to calculate gradient. You're going to use a graphic map scale, which is present on your map. You will find it here in the corner of your map. You're going to determine the change in elevation for a certain distance by counting the contour lines. Now, if you don't have a ruler, you can use a piece of paper, line it up with your map scale, and if they ask you, for instance, to estimate 5 statute miles, you would use this amount of the map scale, mark that on the edges of a paper, and then lay it down on your map, count the changes in elevation by counting the contour lines. So for this map example, in the red area that I've shown here, there are 13 contour lines, and each one is 200 feet. So that's a total of 2,600 feet, and that would be your change in elevation. Couple of tips: use the dark lines to help you, and just be careful and slow about it, counting each one. If you were to give me an answer that was 1 or 2 or even 3 contour lines off, I'm not going to mark you down. This can lead to user error, certainly, but I want to make sure that you do understand the procedure, so that's what I'll be looking for. You're also going to make a topographic profile, and this can be very complicated. It is a higher order skill set where you are trying to think in 3-dimensional terms using 2-dimensional products. So be patient with yourself and read the instructions carefully. What you're doing is you're using the information from your map to create this profile that you see here. And so the line that is drawn on the graph is representative of the elevations, and it should sketch out to look close to a side view of the different mountains and volcanoes that you are considering. So what I'm going to do is I'm going to point you to this YouTube video on topographic maps, and it's going to show you how to use a piece of paper to work with those contour lines on your map, and then how to translate that into a topographic profile. Again, be patient with yourself because this is not a very common way for us to think unless you are an engineer or maybe a landscape designer or something like that. So it is a higher order thinking set, and it does take a little bit of getting used to. If you have any questions, please feel free to email me. All right, I hope you enjoy the lab. Thank you.